Hello and welcome to this video. So in this video, we just want to talk about analogues that you have. We've looked at, we've modeled a mechanical system, or model a couple of mechanical systems, and we also know how to model an electrical system, so particularly an RLC system. Now, a question that could arise is, let's assume I gave you a transfer function, g of s. Many times we'll use g of s to represent transfer function, g of s or t of s. Now, if I give you a transfer function, I tell you the transfer function was, say, 5 divided by s squared plus 2s plus 7. Okay, no, let's actually make this 3, if you don't mind, just so that that system that haunted us for how many videos, we don't forget it very quickly. So let's say we're given a system like this. Question: what type of system is this? Is this an RLC system, or is this a mass spring damper system? Actually, maybe I should write this as MKD instead of MSD. But is this a mass spring damper system, or is this an electrical system, RLC system? Well, that is actually a trick question because we cannot say. It could represent an RLC system, it could represent a mass spring damper system. The point is that when you enter the mathematical domain, when you model an item from a mathematical domain, all that simply happens is that you have represented that system by a system of mathematical equations or by a mathematical system, in which case it is subject to mathematical laws. You can manipulate it mathematically and come up with something. At the point when you're doing all your manipulations, at the point where you're analyzing the system, nobody needs to know what type of system it is. For all we know, this could be an economic system. For all we know, this could be a gear, the shock absorber of a car. This could be so many different possible systems are possible just with this simple model. But then in a mathematical domain, all of that really does not matter. To kind of illustrate that a bit, let's draw an electrical network. This time we'll include an inductor in our, maybe I should have drawn the R first, the resistor first, since we call it an RLC network or an RLC system. So let's say we had this system here and we had our V of t at the input. This is an L, this is our R, and this is our C. If we looked at the currents flowing through, if we use the current flowing through to write our expression, we will have a V of t being equal to L di dt plus IR plus VC of t. Now, this is the same thing as saying that this is L. If you remember what we did earlier on, where I is equal to C dV dt, then this would be LC dVC dt plus RC dVC dt plus VC of t. Taking Laplace transforms, this tells us that V of S is equal to S. This should have been squared. That's the second differential, because C dV dt, by the time I put that in here, becomes the second differential. This should have been S. This should be S squared LC plus SRC plus 1, all multiplied by VC of S. So that the transfer function of this system is given as VC of S divided by V of S being equal to 1 over S squared LC plus SRC plus 1. Now, is this equal to this? Well, you could conceive that maybe one could do some manipulation here and there and arrive at a different constant in the numerator. After all, what you have is S squared LC, but you can see how similar these two are. So this is an RLC network, and we arrived at that. Let's pick a different system. Let's say we had a wall here on the left, so a rigid wall. We had a mass. Let's say we had a mass floating somewhere in the air. Well, not quite floating in the air, but let's say this mass is tethered to the wall via a damper, and let's also include a spring in here. Instead of having it tethered via a damper and a spring, I could have chosen to tether this. I have friction on the ground, but then that's fine. And then let's apply a force F of t over here. This is a mass. I'll call this D and I'll call this K. So based on this system, we're assuming displacement is towards the right. Well, we can just call this x of t. We don't need to put the 1 since there's only one displacement. Now, our f of t will be equal to m second differential of x dt squared plus d first differential of x dt plus kx of t. Find Laplace transform of this. You end up with f of s being equal to s squared, again assuming initial conditions, plus s dx plus k, all this multiplied by x of s. So that gives us our transfer function, x of s over f of s, has been equal to 1 over s squared m plus sd plus k. Very similar. So if I made my k equal to 1 and I just put in values for L and C and R, we could literally not tell what the difference between these two are. And if you looked at these two systems, one thing you will note is that some things seem to be somewhat analogous. Some things seem to be rather analogous. Now, instead of looking at this as current moving, we could look at this as charge moving. If we had thought of this as charge moving, then the relationship between the voltage VC and the charge, your VC will simply be equal to your charge multiplied by the capacitance. No, sorry, this is wrong. Sorry, charge over the capacitance. Sorry, let me just. Okay, so your VC will simply be the Q divided by your capacitance. In other words, a constant multiplied by the charge. Constant multiplied by the charge. Your resistance, your VR, on the other hand, will be, let me scroll up just a little bit so that the R is in focus. So your VR, on the other hand, we know it is current times resistance, but since we're using charge in here, will be your resistance multiplied by the Q dt. Okay, and then your inductance, the voltage across your inductance, L di dt, will become L second differential of Q dt. Now, looking at this expression, let me just simply write this as KQ. Now, a certain constant, or let me say K star, or let me just even leave that entirely. I don't need to write it as KQ. You can see this here, that this is a constant multiplied by Q. Constant multiplied by Q, where Q, if you want, is what is flowing through the circuit. You could think of this system as effectively being a mechanical system where 1 over C is equal to your spring constant and your Q is equal to displacements. If you think of it that way, then your R will be equivalent to your D, your viscous damper, coefficient of viscous damping, and your dq dt will be the same thing as dx dt. Your L will be analogous to your mass. Your inductance will be analogous to your mass. So literally, when you have a mass spring damper system, you could represent your M as an L, as an inductor. You can represent your spring as a capacitor, and you can express your viscous damper as a resistor. You could express it that way so that this is actually analogous to what you have over here. These two are analogues of each other, and it is possible, instead of analyzing a mechanical system, to redraw that system as an electrical network and now analyze it. It is possible to do that. We don't always do that, but it is actually possible to do that. Just bear in mind that your mechanical system and your electronic system, they tend to be analogues of each other when you think of them in the mathematical domain. But one other thing to bear in mind is just the fact that with systems, generally, once we model any system, once we enter the mathematical domain, we generally become agnostic to what the actual system was. When we're done from the mathematical domain, so say for example, we were trying to engineer a system that will have a reliability of a certain value. We have done our modeling, we've come to the mathematical domain, we've tweaked it, we've played around with it, we've come up with what we want. To now implement that as an actual physical system, we now need to understand what the original system was and how to take that mathematical model and go back into the real world, if you want, to become an actual system. So say, for example, after designing a system, we have a shock absorber that existed already. We have a car that exists. We want to design a shock absorber for it. When we are done, we arrive at a certain shock absorber that has shock absorber, the transfer function of the shock absorber, we arrive at it as 3 over s squared plus 2s plus 7. The next question will be, how can we implement this value as a real system? To implement this value as a real system, one thing we might think about might be, okay, let's have it as an electromagnetic shock absorber. If it's an electromagnetic shock absorber, then maybe we need a resistance in there. Maybe we need a capacitance in there. Or then we need an electromagnet. Okay, how do we model the electromagnet? Or maybe we just want it to be a mass spring damper system. If we have it as a mass spring damper system, then we have a spring in there. We probably have a damper in there. By the way, in case you don't know this yet, a shock absorber is made up really largely of these two things, a spring and a damper. If you check every shock absorber, you have a spring and a damper. In fact, if you walk up to any car and check, if you have one yourself, if you walk up to a random stranger's car, the person will probably be wondering what you're doing. But if you check any car, you see that you have a spring. The spring is always usually obvious, but there is also a damper. And we will talk a little more about what damping does, what a damper does. But you have a damper in there as well, and you have a spring. So your mass, obviously, it has a mass as well, but the car itself has a mass. So we don't really talk about the mass of the shock absorber, though the shock absorber does have its own mass, and you need to factor that into your equations when you're running. So if you wanted to implement this, you probably think of a particular mass of a certain with a certain constant, a damper with a certain constant. You can now put them all together with a mass that you have, and you arrive at the transfer function that you get, and your system, the car, responds the way you expect it to work. So that'll be it for this video. See you in the next one.